All right. Well, according to me, it's 10 o'clock, so I'll let you I'll hand over to you, Francesca.
Yes. Diane, I will wait maybe on your side when you see, because I cannot see if people are.
I'll start the broadcast now. So you ready?
Yeah, I'm ready. Just give me a sign when. All right, good morning. Good morning, everyone, and welcome to this very exciting webinar on what comes after CMOS, followed by debate with three world-renowned experts. One is Dr. Paolo Gargini from California, who is heading the IEEE RDS, so the new international roadmap for semiconductors and systems and devices. Professor Michelle Simmons from UNSW, so University of New South Wales. I don't think she needs a lot of introductions. She's a leader in quantum computing, particularly in silicon, and we'll have a fantastic talk from her, as well as Professor Michael Führer, who is from leading the Fleet ARC Center of Excellence down in Melbourne, Monash, and is an expert of 2D materials and topological insulators. So it's really great to see so many people dialing in today all over Australia, but also outside of Australia. I saw as people signing in from Singapore, from India, from a lot of other countries. Personally, I'm dialing in from Sydney on the lands of the Gadigal, who are one of the seven major people of your nation. So I would like to acknowledge them as the traditional custodians of this land and pay my respects to the elders, both past and present. So just a quick introduction to myself and this webinar. So I'm Professor Francesca Jacopi from UTS, the University of Technology, Sydney, and I'm also the inaugural chair of the Electron Devices Society chapter in New South Wales, which started this year, 2020, this very special year. This event also marks our official chapter inauguration, and it was meant to be an in-person workshop, but of course, as you all know, the problem of COVID has stopped that from happening. And so we're having this very wide webinar, which allows many more people to join in, so it's not such a bad thing in the end. So as you probably all know, IEEE is one of the world's largest professional association dedicated to advancing technological innovation and excellence for the benefit of humanity. With more than 395 members in more than 160 countries, IEEE creates an environment where individuals collaborate locally and globally on world-changing technologies. The Electron Device Society, EDS, of IEEE, of this chapter we're part of, has a focus on all electron and ion-based devices in their classical or quantum states, using environments and materials in their lowest to highest conducting phase in simple or engineering assembly and interacting and delivering all sorts of different signals, photoelectric, electromagnetic, electromechanical, and such. So the Society has sponsored numerous chapters around the whole globe to further activities and communities around electric devices, and this is exactly what we've done here, and we're very proud to have one served now in New South Wales, where there's so much activity in the field of electronic devices. So I will moderate this event together with my colleague, Dr. David Courty from University of Wollongong, and also part of Fleet. And I would also like to acknowledge Errol Hunt and Diane Ruka from Fleet for all their help in getting this webinar off the ground, which is quite a feat, especially with quite a large audience. So before we leave the floor to this first speaker, which is Dr. Gargini, a few housekeeping items. So to all of the audience, for questions and answers, please do use the Q&A feature of Zoom that I'm sure you will be familiar with. And all of the questions are going to be moderated before they appear. So please post anything you'd like to ask in the Q&A window and identify yourself in the question after each speaker. So I thank you again for joining in. in such big numbers to this webinar. And at this point, I would really like to introduce our esteemed colleague, Dr. Paolo Gargini, joining in from California, who would actually talk to us about the role of the roadmaps in shaping the semiconductor technology and industry. So I'd like to leave the floor to, I'll mute myself, and I'd like to leave the floor to Paolo. Please, Paolo, join me all to welcome Paolo's presentation. Paolo, is over to you.
Yeah, give me back the screen. I'm looking at Diane's screen. Can you see the screen? Hello?
Yes, we can see it. Yes, we can see it, Paolo.
Okay, thank you. Okay, so thank you for the invitation. I'm going to give a very broad overview. There are many foils, but I'm not going to talk about the details. The main point is it's difficult at times to realize that things are changing, and you have to look at it with a broad view. And in my experience, there are about 25-year cycles. They succeed each other. And so it's important to spot this inflection point. In many cases, people believe that things are going to go in the same way for forever. And then they are surprised when all of a sudden something comes to a halt. But in reality, this doesn't have to be this way, because if you utilize a roadmap, you can see this inflection point like 10 years in advance. And so you can put programs in place to avoid these situations. These are all the roadmaps that I've been participating in. I had my regular job at Intel, but this was also a side activity that I found that was very rewarding. And you can see that it began with the National Technology Roadmap that was US only. Then when I became chairman in '98, I made it international. And then when the horizon of the roadmap had extended even further, the roadmap was moved from SIA, the Semiconductor Industry Association, to IEEE. And we are just placing this week on the web the 2020 IRDS. Already 708 chapters have been placed there. So fortunately, the roadmap of the semiconductor industry began as far back as 1965. Gordon in 1965 made an extrapolation that you can see if you're a scientist is very gutsy, because with 5 data points, he projected 65,000 transistors 10 years later. And when I first came into California in the early '70s, only local people in Silicon Valley knew about this. Not too many people paid attention. But then, much to the surprise of everybody, in 1975, this came true. And you can see actually that initially bipolar devices were the key element that he used, but then there was a transition between 65 and 70 to MOS. And indeed, by 1975, the 65,000 transistors were viable. The other thing that he did, he identified from the very beginning that there were 3 major contributors. The number 1 contributor was the architecture, the contributor 2 to the 7th. And the second one was really scaling the dimension, that contributed 2 to the 5th. And also manufacturing, that means the ability to have larger dies, contributed 2 to the 4th. Many people believe there is only scaling and always forget the other 2 contributions. But as you can see, without this contribution, it's impossible really to stay on Moore's law. And what Gordon said is, at this pace, we're going to go on a doubling every 2 years. And indeed, this principle was, eventually you can make anything you want, because you're going to have so many transistors that no matter how complex the problem is, you can solve it by throwing transistors at it. So after this, for 20 plus years, everybody had a very easy life. Essentially, it was very easy to scale down, a transistor. And if you think this is just a sketch, this real life, this is a cross-section of real transistor. It's not the same photograph shrunk 3 times. It's really transistor, and you can see they were very similar. And in this way, since they were smaller, they could go faster. You could place more of them. And since you could place more of them in a square centimeter, it was cheaper to sell integrated circuits. But something was going to come very abruptly. And this is my foils from the 1997 roadmap, in which I'm showing the thickness of the gate oxide. And at that point, it was about in the 4 nanometer. This is around 1994. And then you can project that every generation you eliminate 2 or 3 pseudo, monolayers. And so by 2003, we were going to have a major problem. There was enough time to fix the problem, but if we had continued at the same pace, we would have run into a major, inflection point. In addition, you can see from this one, if you show on the left-hand side the thickness of the silicon dioxide, and as it getting thinner, the leakage through the gate dioxide becomes higher, actually almost 1 decade per generation. So this problem also was becoming very difficult to deal with. So we were coming to a point, for those of you that were around 1997 to 2000, where everybody was projecting the end of the electronic industry because we couldn't go any further. And the point was, since we had seen this coming, we have put things in place to deal with this crisis and dealing with the next 25 years or so. So first of all, this effort was very broad. And so it was necessary to do not just people in the United States, but people around the world. And so this was one of the elements of starting this international, roadmap. And, at the first meeting, I presented this plan for the next 20 years. And many people thought I was putting a coaxial cable and not a transistor on the board. But I simply wanted to show that the structure was going to change drastically. We needed to replace the silicon dioxide with the high-K insulator to have a metal gate completely surrounding this. We needed to manipulate the bands and introduce strain and many other things that at that point seemed quite complex. But fortunately, the university, the research institute jumped on this problem. And you can see, even though the inventions have been done in the, as far back as 1997 or the mid-90s, we began placing money at the rate of 10, 20, 30, $40 million and so forth between 1998 and 2000 everywhere around the world. And in 11 years, half the time that you normally it takes to go through one of these inflection points, we had come to a viable solution. This was not the only problem, because there was also an architectural problem. These have been identified as far back at the late 80s. The point is, as you build a microprocessor, you increase the number of transistors, and you want them to work at a higher frequency, progressively the dynamic power keeps on increasing. And at that time, every 2 years, the number of transistors would double, but the frequency just about double. So we have projected in a very simplistic way, if you, instead of using a single core that runs, let's say, at 1 gigahertz, you have 4 cores where the total number of transistors doesn't change, but each one of the cores runs at 250 megahertz, then you cut in the power substantially down. And also at that time, we said, they're going to have so many transistors that we can build some multimedia object that we didn't know, that it would become the iPhone. So if you look at the sequence, for instance, in 1999, the power was 51 watts, 1.3 gigahertz, and then it will progressively go to 1.9, but 72 watts. And by 2003, when the frequency just about doubled, the power reached 115 watts. That is about the limit that you can have without using water cooling. So what we had projected, came to fruition. Not that we liked it, but we had a big problem around 2003. So instantaneously, you can see 2005, 2007, there was a switch to, on the far left, you can see to 2 cores. And then you can see where the frequency maintains a similar value than before, but the power is cut just about in half. So the simplistic solution was viable, even though it doesn't apply in all cases, because not all the programs are 100% parallel. It's a mix of serial and parallel, but at least we were able to stretch this architecture for another 10, 15 years. So, however, we found 2 solutions that were limiting the problem, not eliminating the problem. So at that point, in the United States, there was the National Nanotechnology Initiative that was headed by Mike Rocco. And so, after the first 2 or 3 years of excitement, I organized a meeting at Intel, and Mike and I decided to begin working together as opposed to funding program independently. And this led in 2004 at the NRI, in which formally we launched, a worldwide program on novel devices. There were no CMOS devices, but something beyond. And so this was the position of the problem. If you look at the high power CMOS running energy about 100 plus femtojoules and delay of 10 to the 3rd picosecond, or the low power that was running slower, 10 to the 4th, but consuming 1 order of magnitude less power. And we wanted to find something to reach the red star in the lower left corner. So we asked the professors and so forth, and I went around and asked with all the famous professors, and they talk about the problem was that the tail of the distribution that you see in the right side, it's a long exponential tail, and so it goes over the barrier even when the device is off, and so you always have leakage. And they suggested that you need to change this dramatically. And so if you move your electron, essentially you change the source from N to P, then your electrons will reside in the valence band. Then you kill the leakage, but then if you want to go over the gate, at this point you have added 1 volt. That doesn't seem like a very good solution for under operation. And the idea was, why don't you tunnel through? So I'm going to leave this to this because at this point, because there will be a more detailed explanation in one of the next talks, but this was the idea. And you can see that we had to stop frequency because the industry wanted to keep adding functionality. So the number of transistors was going to go up, but the frequency had to stop. But you can see, if you look at this on the right-hand side, transistor could work at 200 gigahertz, but we had to hold them back. So the misconception was, oh, transistors don't go as fast as before. That was not the problem. We couldn't let them go as fast as they wanted to, because otherwise we will melt the die. So we needed to have another solution to pack more transistors. And so in 2013, I simply used very similar scheme that I had used for the gate oxide, even though this gate, the node name, as you'll see, are not really correct. I say, well, at this pace, beyond 2021, we'll be at a 1 nanometer, so we cannot proceed any further. And this was simply to go to the next slide. But unfortunately, the economy stopped at that place. And besides misspelling my last name, they reported that I had forecasted once again the end of Moore's law by 2021. That was not the point. What I wanted to forecast is that we needed to go vertical very aggressively. And this is much, much easier because if you remember the initial 6 points, the structure plus the 3 rectangle, the 5 rectangle, these we already had a lot of experience. So at this point was a question of experiencing with the structure of the transistor. And the first people that really understood this point were the people in flash memory, because flash memory were really under pressure for cost. The memory normally sell for much lower prices than logic. And you can see the blue line, they were going to smaller and smaller feature with more expensive lithography. And instead, by going to multiple layers, then they could relax lithography substantially. In fact, it goes in the opposite way. To date, flash memory in the 100 or so layer are commercially available. So in the meantime, we moved the roadmap under IEEE because now we were completely engaged between device structure and system architecture. And so it was necessary to go beyond the limit of simply the Semiconductor Industry Association. Now, you might have seen this picture that is very famous. Essentially shows, let me build it up. Okay, if you look at the power, in orange, it has to stay around 120, 130 watts. And to do so, if you look at the green, the frequency levels off in the 5-6 gigahertz. Now, you can increase the number of cores. You see, in this case, you can go 50 cores or 80 or so forth. And you still have some improvement in the performance, but not as much as you used to have in the 90s. On the other hand, everybody say, oh, this is happening because Moore's law is close to the end. Now, you can see Moore's law in red that is completely oblivious of all these other considerations. It continues to add the number of transistors. So it was time to solve the architectural problem really from the roots. So it takes Bill Dudley, professor that was the head of the Department of Computer Science at Stanford, that decides to go into the industry, go to NVIDIA. NVIDIA was producing all these imagers, and so they have millions of parallel paths. And so what he did, this is his slide that he gave me in 2018. Essentially, you can see the old blue line that is leveling off because it's enclosed into the architecture of a microprocessor. But when you find an application like face recognition or some of these other application in which you can use the full power of parallel paths, then in that case, the performance progresses at the same rate or even better than in the 90s. And you see the red vertical line. These are the same type of transistor. They are not different, but you're not really getting the performance out of the transistor because of the architecture. That's why we had to move to the IRDS and mix architecture and transistor to really get the best performance. In the meantime, our friends in the university and research working on the tunnel transistor have made progress. You see the red circles, they're lower than the green. That is the reference of CMOS. And if you look at this chart, we actually trial different kind of devices. So we have a constellation of devices that we can pick and choose depending upon what we want. But the structure is still a little complicated. And so the industry has not completely embraced it, but progress continues to be made. So we come to the point that we could take, combine, architectural and device solution and combine them together. And so you can see that now the structure, instead of making the gates smaller, it's time to stack them up, like you can see from the far left, then take the transistor in the middle completely vertical, and then build an array of vertical transistor. While the flash people had embraced very quickly this approach, the logic people are always very conservative. Nevertheless, you can see now that in the last couple of years, many of these structure where you can see 3 parallel transistors, one on top of the other, there is really a practical implementation of the sketch that I had on the previous page. They are being reported in conferences. And so that's why I have put 2015 to 2025 for this transition. 2015, memory began. 2025, when I expect some of the logic people will present something. But this is not the limit. Actually, you can combine, multiple approaches. In particular, every time you go out from a logic die and you go through interconnection to another die that is memory, immediately you lose a gigantic amount of time. And so by placing multiple memories, especially memory like magnetic memories of thin carbon nanotubes, memory that consume very little power, then you can actually make everything more compact and actually be more efficient as far as power consumption. So with this, we sailed through the 75 to 2002, just blind scaling. Then we began 2003 to change the transistor with the FinFET. There was a half step towards vertical dimension, changing the gate oxide with the new high K, hafnium, zirconium, all these elements. And then, we now 2015, 2025, we are in the transition where everything is going to go vertical. So, but we need to keep our eyes open for the next cycle. Eventually, no matter what we do, physical limits will be reached. And so we need to be ready for this. First of all, let me say when with these limits will really be reached. The definition of nodes is derived from the sketch on the left-hand side. You see the metal pitch, and we define the half of metal pitch as the definition of node. And this half of metal pitch in the 80s, 90s, and so forth, was almost the same that the poly width. And so this was the real definition. But then company, trying to show that they were ahead of the others, began to use definition that was the average of the gate and the half pitch, making the gate smaller to make transistor faster. Then some companies say just the gate length, then the fin pitch and so forth. And then at some point it became some small number that was simply 0.7 of the previous node. So if you look at the numbers, especially the one on the far right, 7, 10, and so forth, they have no meaning with the reality of what the circuit is. It just, after approximately 2011 or so forth, these numbers are simply PR numbers used by different companies to advertise what they do. So if you want to have the real numbers, these are the real number using the right definition. So today we are not in the 7 to 5 nanometer generation. We are in the 18 nanometer generation. And if you go on the web and you look at the IRDS, at the top, we have both numbers, the real numbers, we have the gate numbers, and we have what the industry calls the nodes. I didn't want to spend time on this, but I want to tell you, however, that around 2029, 2030, we'll level up at 8 nanometer, 7, 8 nanometer, at which point scaling will not help us anymore. So we had to find new ways of improving functionality. And so I tried to explain already in 2017 the situation, but it was like a voice in the wind. But I went to visit with Gordon Moore in 2018, and I said, Gordon, there are another 10 years that we can use your law. And Gordon was very pleased. So the number of integrated circuit, the number of components keeps going up. The industry is very healthy. You see when a major inflection point for product point of view, whether it's PC, iPhone, iPad, the internet in this moment, Zoom, there were 10 million of Zoom connection in December. I look at the number in April, there were 300 million. And the PC normally in the first quarter goes down by 2-3%. And sales on notebooks went up 13%. So, actually we had a positive impact. But we now need to use the fourth dimension and to manage the next 25 years. And there is time to put things in place. And this one is the multi-bit scaling. It has to be in full swing in 2040, but we're going to aim within 2035 or so to have prototypes even sooner if it's possible. So there is a world that has promised to do all this. We just had to learn different names like qubits, coherence, entanglement, and so forth. And the promise, why are we attracted to this? Because with scaling, we had an exponential growth. But with the quantum world, the exponent is exponentially growing. So it's too good to let it go by. However, everybody says that it's very difficult to keep things stable coherent in the quantum world, you need to have at least 1 million qubits so that your error is below 10 to the minus 3. So I just extract simple elements. What does it take to make 1 million qubits? So if I look in the back history, in the 60s, 70s, 80s, there were many families of logic, but eventually the simplest, that is CMOS, emerged as the most efficient. If I look at the situation in the last 5 years, everybody can do some quantum publication because there are many ways in which things can entangle and so forth. So it's very similar to what I remember, the 70s. And so I wanted to calibrate the real status. So in 2017, IBM published these results in which they made the error of leaving the 1 millimeter line. So if you see the two slanted red lines, I put them on top to measure this. These are two 10 millimeter line, and there are 16 qubits. And then I checked with my friends at IBM, said, no, the qubit itself is only 1 millimeter by 1 millimeter. I said, okay, so let me calculate what it takes to make 1 million qubits. So if you go from the top, you have 10 millimeter on the side, means that the die is, whoops. The die is 100 millimeters square. So it's 6 millimeters square per qubit. You want 1 million. And so you look at the area and you look, it's 2.5 meters on the side, very large. If I use the 1 millimeter square, saying that you can put all the other circuitry on top in some other way, it's 1 meter on the side. So the die is very large at this point, but it shouldn't be surprised because this is the 1959. The transistor is 3/4 of a millimeter. So if you wanted to make something with a million transistor at the time, it would have been 0.5 meter by 0.5 meter. So it's comparable. So let's see how we get to the 1 million transistor. We put together, a lot of equipment, and the equipment have become more and more complex because every year we needed to make something smaller. But this equipment exists and now can be made available to the quantum computer industry. So right now, an example, this is the Tesla V100, 815 millimeters square, 21 billion transistor. And so if I take this element, if we don't do anything, this is what I see as the timetable to reach the 1 million transistor, at least with one approach. So, on the left-hand side, 1925, the first set of patents from Lilienfeld on how to build a transistor. They apply 100% on the MOS. And then the first idea, not just simply there's this room at the bottom, but how would you build a quantum computer? And this 1980. So then after about 20 years, the demonstration of the transistor. After 20 years, the demonstration of something that looks like a quantum entanglement. And then by 1965, in the Gordon Moore paper, there are 50 transistors, and IBM was saying we can make 50 qubits. So I feel like I'm calibrating the numbers correctly. Then on the left-hand side, what happened, there was the commercialization of MOS. There was a structure, the silicon gate, that was very efficient. This leading structure has not been selected yet. But 65,000 transistors came in 75. So this will put the 65,000 qubits in 2027 and 1 million in 2037. So without discussing D-Wave or some special application, I'm just taking the basics. So can we do anything with what we learn and apply for the semiconductor industry, applying to the qubits? And so in 2018, I began publishing something and putting in my presentation incentives, try to build the bridge between the research environment and the engineering environment to see if we can accelerate at some point in the future this cooperation. So the point is, instead of taking any qubit and see how we make 1 million on them, the MOS was essentially the simplest solution. So what would be the simplest solution that has the highest probability of reaching the 1 million qubits? So now we have to go through this list like we did before. And I tried to use a very basic principle that is called Occam's razor. Essentially, among competing hypotheses, the one with the fewest assumptions should be selected. So at this point, I had my guideline. So the simplicity of transistor was obvious, just looking. It simply has a source, a gate, drain, very simple. And so I was looking for the next one. So in 2005, I was contacted by Robert Clark, and he was proposing a new approach using silicon that was very interesting. We had several conversations, and at some point the paper came up that I saved, and I look at the two structure, and I say, these are equally simple. So in my mind, these are very promising. And then I look at some of the numbers. So what does it take? It takes 25 nanometer holds every 60 nanometer. I say, well, in 10, 15 years, we will be able to do this, not in a very complicated way, but just with standard manufacturing techniques. Additionally, another problem was you have to accurately place the transistor on top so that you can interact with the qubit itself. And so I say, well, let's see what we can accomplish down the road. And then I see, and we'll hear some more in the next presentation, that this approach has been enhanced and magnified and so forth. But if I look at the dimensions, we're still in the same ballpark. I saw some results on 13 nanometer, but it's in this range and it looks very simple. So can we do any of this on an industrial level? As I saw the video, it's very complicated to place these atoms in the right place and so forth. But do we have in principle, the technology to do this? So could we, if we were given this recipe, could we place things in the right place and the right space? So this, in 2018, you can see these are 13 nanometer lines and spaces. This is in the research environment. And you can see that the dimensions start to be in the ballpark of what you need to do. This is essentially the end of last year, 16 nanometer lines and spaces, 18 nanometer contact holes. It starts to be in the ballpark of what I saw, in those papers. And so then the other point was placement. This is actual real results. The top one shows the placement, the overlay placement. If you use the same scanner, and you can see it's less than 1 nanometer, X and Y, 0.81, 0.57. And machine to machine means normally if you use 5 machines, and you intermix all of them, and you can see you degrade to about 1.2 nanometer. So it tells me that the features, the placement, the crude stuff, the mechanical stuff are already available if somebody gives us the right recipe. So my conclusion is, we are now, in the world of the 3D power scaling, where all the structure from memory to logic are going in the vertical direction. We have many new architectures that have really embraced, besides the heterogeneous integration or placing dies one on top of the other, or parallel processing and so forth. And there are, memory, we can do logic in memory, and you have to do computer learning. So there has been a major connection between new, especially memory devices that didn't exist 15 years ago, and architecture. But we see, in the 2030 to 2035, we'll reach the limit of all these elements, and we need something else to enhance the functionality. And so this already we have put a name. There is the multi-bit scaling, in which you can have multiple bits in the same location. And I hope that we can build bridges with the research community to accelerate this connection. So with this, that's my vision of the future.
Paolo, thank you very much for the wonderful talk. We really appreciate you taking the time and coming to give us some of the insights in how the industry has evolved over the decades and how it's continuously succeeded and where it may be heading. Much of what you've talked about really resonates with one of our projects in the Center for Future Low and Energy Electronics fleet here in Australia. And I'm sure we could have some good discussions about that. But I'll remind everyone that we're going to hold off the questions and answers until the end of the session after all three speakers. So please use the Q&A feature at the bottom of Zoom to post your questions, and we'll select some of those for our speakers at the conclusion.
I would like to introduce our third speaker, which is Professor Michael Fuhrer. He's leading the Future Low Energy Electronics Technologies ERC Center, called also Fleet, and he will give us a perspective on how to use topological insulators for future electronic devices with low energy consumption. The floor is yours, Michael.
Okay, thanks very much. We've had two fantastic introductions to computation beyond CMOS, so I hope I won't repeat things too much, but what I'm going to try to tell you today is a slightly different perspective, and we're focused on reducing the amount of energy that's used in electronics, and I'm going to talk about one of our projects towards that, which is to use topological insulators. So what's the challenge? I think this has already been laid out a little bit. From the consumer perspective, we have these fantastic computing devices, and we expect a lot from them. So, everybody carries around a little supercomputer in their pocket these days, and that computer forecasts the weather, it delivers sound and video from around the world, predicts their route through traffic. And, we expect our computers to, very soon or even now translate speech in real time, drive our cars, deliver us to other places in a immersive virtual reality. I think all these things are coming, of course. So they're fantastic advances that we've had that have changed our lives due to computing. But at the moment, information technology is using about 8% of the electricity on Earth, and that's doubling every decade. So these devices that we're using, often the energy that's used to do the computations that are done is not being dissipated in the device because the computations are being done somewhere else. They're often done in servers somewhere, and those servers use an enormous amount of energy. And that energy, if you're in Australia, will come often from a coal-fired power plant, and so there are consequences of that energy use. The energy used by data centers alone, which is about 1/3 of the energy used in IT, is significant. So this is it's hard to get really quantitative numbers on this, but this is a couple of different estimates that were done recently. So about a decade ago, it was 1% or 1.5% of global electricity, and some 1/4 to 0.5% of global greenhouse gas emissions. A decade from now, it could be 13% of global electricity just in data centers, and that would be 6% of global greenhouse gas emissions. And so, it's hard to say where we're tracking, but this is something that is increasing, and we it seems to be, while other sectors are becoming more efficient, this sector seems to be increasing rapidly. So Paolo gave us a really great introduction to silicon CMOS, so I can't say too much more. It's an incredible technology. We have fabricated, and when I say we, I mean humankind, has made 10 to the 22 transistors, or probably more, have been manufactured. Because of exponential growth, those 10 to the 22, the majority of them were probably fabricated in the last 2 years. It's more of any individually addressable object that's ever been made. It's an astounding accomplishment. We're really, really good at making transistors. This is because of Moore's law, and I put Moore's law in quotes because I really mean, as Paolo pointed out, the effort to keep the Moore's law on track through road mapping and to follow this trend in increasing ability to make smaller, faster, and more efficient transistors. And so what's been on track is that in general, the transistors have shrunk in length by 30% and in area by 50% every 2 years, doubling the number of transistors that you can fit on a chip. Due to this growth, the capacity globally to compute has grown by 60% per year. So the number of computations we can do on the planet grows at 60% per year, and it has for decades, which I think is astounding. So it's hard to imagine anything that grows at 60% per year, and then to grow at that rate for decades is really incredible. So, and you might ask, how can that be, right? I mean, computations use some amount of energy, even though it's a tiny amount. So how can we do this at 60% per year without consequence? And for a while, we could do it without consequence, and that was due to the scaling that Paolo talked about. The energy to switch a transistor is the energy to charge up the gate capacitor, so it's 1/2 CV squared. And when we were able to scale transistors geometrically, it's a so-called Bénard scaling, we would shrink the length, the width, we'd shrink the gate oxide thickness, and we'd reduce the voltage. And the energy actually shrank by this, whatever this scaling factor was, Q. And so every 2 years, we would shrink transistors by 30% to 0.7 of their original dimension. And the energy would be only 35% of the energy that to switch a transistor. And so every 2 years, we're doing 60% more computations a year. So 256% of the computations that we did 2 years ago, but it only requires 35% of the energy, and 35% times 256% turns out to be 95%. And so we can actually do 60% more computations per year and actually do them for less energy, which is amazing. And it allowed us to have this free lunch for decades. That ended at, I've got 2005, Paolo had 2002. I think that's, somewhere around there. We stopped this kind of geometric scaling. And so there was a bit of an inflection point. And that has meant that while we've been able to get the same kind of power and performance from chips, that the individual devices, when they switch, the individual transistors are using more energy. And so that energy is going down, but not as fast. And so now it might be 50% of the energy, switching energy in each new generation. And so, the energy use in computation is going up. If our simple math would predict that it's 128% more energy over 2 years, so about 13% per year, and that's close to the estimates that I showed you previously of about 10% per year increase in the amount of energy that's used in computation. So there's no more free lunch because of this end of scaling. And so where are we now? There are many ways to look at this Moore's law progression of technologies. We've gone through different eras of scaling, as Paolo pointed out. When the Fleet Center started in 2015, when we started to organize, there were actually 4 companies worldwide that could manufacture at the present state-of-the-art node then, which was 14 nanometers in a nominal dimension. And at the moment, well, in 2019, last year, we should nominally have moved to 7 nanometers. Samsung and Taiwanese Semiconductor Manufacturing Corporation were at 7 nanometers. They had plans, they've announced plans for 5 nanometer manufacturing. Intel is at 10 nanometers, and they seem to be apparently stuck and less able to progress. And Global Foundries actually gave up. So they gave up their plans to move to 7 nanometers. So we've gone from 4 companies in the world that could manufacture the state-of-the-art devices to 2 and possibly a third. And this was, of course, will eventually we will plateau, and so devices will stop shrinking in their actual dimensions. As Paolo pointed out, these future nodes are actually kind of converging to a point around 8 nanometers in practical size, and so scaling eventually will run out at the device level, and at that point we don't know what will happen, but we think that at least at the individual device level, the energy that's used to switch a device is going to stop decreasing. So at the device level, the energy efficiency will stop. And so if we want this 60% more computations every year, we want that to continue, this is going to require every 2 years, 256% of the energy that we used 2 years ago. So, 60% rise in energy per year. Of course, that's going to be unsustainable. Some of that will be offset by the fact that we'll have more parallelism. We'll have ways to use specialty processors to do certain processes more efficiently. There will be ways to squeeze a lot more efficiency out of the transistors that we have. But at the basic device level, we need to switch transistors on and off to do computations, and the energy that that's going to take is going to become constant. Okay, so the question then is, how do we sustainably continue this information technology revolution, which has enormous benefits to society? So we do want to continue that, and so we think eventually at the device level we'll need to find more efficient devices. So there's many solutions to that, this idea that we need lower energy electronics. It's worth saying that the fundamental limit is still far in the future. So even though we think that Moore's law will bring silicon to a practical end in terms of what we can achieve, the fundamental limit is still much better. And so there is a fundamental limit to irreversible computation at room temperature, and it's about 3/1000ths of an attojoule. And current transistors are many orders of magnitude from this limit in terms of energy, switching energy. And so there is room for improvement. There's no physical fundamental principle that forbids that. There are many strategies, like quantum computing. This low energy electronics has a number of strategies that are being pursued. Some of them involve using state variables that are not charged, such as spintronics. Quantum cellular automata involves moving charge around, but not in transistors. Reversible computing is an idea, so this gets around this irreversible computing limit. And quantum computing is a subset of reversible computing, and so quantum computing could actually inform better ways to do classical computing. Superconducting computing is another possibility, which is known to use very low energy, but at the moment it only works at low temperature. We've chosen to focus on things that are closer to conventional field effect devices, and so again in that transistor, the energy to switch a transistor then is going to be the energy to charge up the gate, and the strategy there is we already know we can make the transistors small, but we need to make that voltage smaller. And there are many ways to do that. As Paolo mentioned, you can use an intraband tunneling transistor to reduce the subthreshold swing. You can use, there's something called a negative capacitance FET, or you could take advantage of an electronic phase transition in the material, which could switch very sensitively at low voltage. And so there are many versions of this such as the MOT-FET, bilayer superfluid FET, etc. So the fleet approach to this, we looked at this, and what we looked at is we looked at what was going on in the fundamental physics community and material science community, where we found that there are some new mechanisms for electronic conduction. They're interesting in that they can involve electronic conduction without dissipation or without resistance, which is an added bonus. And we wanted to focus on mechanisms that could work at room temperature. And so we focused on three things. We focused on topological insulators, which have edge modes, which can conduct without resistance. Exciton or exciton polariton condensates, which are a kind of superfluid, but a superfluid that can work at room temperature. And non-equilibrium phases, where we induce either topological or superfluid states by a time-dependent field, such as a light field. And then we want to make a switch, and that switch would either be based on this quantum phase transition from a trivial insulator to a topological insulator, which I'll talk about in more detail, or this collective electron phenomenon, exciton condensation or superfluidity. And so those are known to be sensitive kinds of switches, so they could work at low voltage. I'll talk about only part of this today. It's a big center, and so I'll talk about parts that I'm personally involved in terms of the research. And those are looking at topological insulators and topological edge modes, and then switching the topology on and off. And so I'll explain what that means. Okay, so topological insulators. So, 15 years ago, we thought there was only one kind of insulator in the world. Insulators are things with band gaps. So semiconductors are just insulators, but they have smaller band gaps. So gallium arsenide we think of as an insulator. And the different kinds of insulators were only distinguished by having different sizes of their band gaps. And then we realized actually there's a kind of limit down at zero band gap, where the band gap goes just to zero, and then sort of zero band gap insulator. And that's kind of a special point. And those things now we call topological Dirac semimetals. And so one example is graphene, which is quite famous. It's like a zero band gap insulator. It's a single atomically thin layer of carbon. And the really surprising thing is that we realized, physicists realized, that there's actually something beyond this. So if you manage to invert the band gap and make it negative, you get something really funny. You can get something that is effectively an insulator again, but it's a special insulator called a topological insulator, and it's special because it has extra states that live on its edges that are metallic. And so it's insulating in the middle, but the edges or the surfaces are metallic. And so there are two-dimensional versions of this and three-dimensional versions of this. In 2D, you have something that's insulating in the middle, but it has edges that are one-dimensional wires that run around the edge of the material, and they can carry current. Turns out they carry spin polarized current in opposite directions, and because that current is spin polarized, it's protected from backscattering, because that requires a spin flip, and that is difficult without magnetic disorder. And three-dimensional topological insulators are then insulating in the bulk in the interior, but they conduct on their two-dimensional surfaces. And again, they have this spin that is coupled to the direction of the momentum of the electrons. So the idea that we're pursuing in Fleet is to use these topological insulators to make a transistor. So what we want is a three-terminal device. So where a gate uses an electric field produced by a gate controls current from source to drain. And so we do that by applying a voltage to a gate, which would create an electric field, which would transform the channel material from conventional insulator to topological insulator, and then allow current to flow along these topological edges. And so that's the vision of the device that we have. So we're not the only people to have envisioned this kind of device. So there are numerous proposals for mechanisms by which this would work. Topological crystalline insulators, you can break symmetry with an electric field and open a gap. In the 2D quantum spin Hall systems like silicene and transition metal dichalcogenides, it's been shown that you can, there are various mechanisms that can drive a material from conventional to topological with electric field. And in the materials that I'll talk about today, topological direct semimetals, this can be done as well. We've been able to recently show that this makes a better transistor. So there's a reason to do this. So this kind of transition, this way of opening a band gap and turning the material off, can open a band gap faster with a gate voltage than you could raise a barrier in a MOSFET. And so you get an advantage, and that advantage comes about because of spin orbit coupling. It's not there in a material that has no spin orbit coupling. And so it's an inherent kind of topological effect. And it allows you to enhance the subthreshold slope of a transistor. It looks like for sort of reasonable parameters, material parameters, you could get a 30% enhancement, but there's no limit to it. And I think with really careful material design, it could be even higher. And so there's a reason to kind of look at this kind of transistor. Okay, so where to look for these materials? So we set out to look at, again, at materials that were kind of in the middle of this, this phase diagram between positive and negative band gap, because those are, we thought, well, they'll be the easiest to push back and forth across this phase transition. And so we set out to look at this topological direct semimetal called sodium-3 bismuth, because it has very, very strong spin orbit coupling, and so it could make a very good transistor. And so this material is three-dimensional. It has these Dirac cones where energy is linear in momentum in all three dimensions. So it's like a three-dimensional version of graphene. So we can, and that material actually was predicted just around the time we started working on it to show this kind of transistor effect. So you can see that if you make the material very thin, 3 nanometers thick, then you can get a band gap. And if you apply an electric field, you can tune that band gap to 0 and then reopen it, but it'll be topological. And so you can get that switching from conventional to topological. And so that transistor effect. This material is very air sensitive, unfortunately, so we've had to design special tools to work with it. So we work with it actually in ultra high vacuum, and we can grow this material, do transport experiments, and measure electrical properties, and do scanning tunneling microscopy all in the same chamber. And so that's nice. It's allowed us to perform some very nice experiments. I'll just show you a little bit of our work on ultra thin material. So this is showing a scanning tunneling micrograph of a film that's, you know, nominally 1 nanometer thick. It has 1 monolayer and 2 monolayer regions of sodium-3 bismuth. Again, the structure looks something like the structure on the right. And we can do scanning tunneling spectroscopy with the STM tip on this material and we measure a gap in the spectroscopy here where we get 0 tunneling current, and that corresponds to the band gap, which is over 300 millivolts in both the monolayer and the bilayer. So the experimental points are in blue here. It's not as big a gap as silicon, but it's quite big, and it looks like this material could be useful at room temperature due to this size of gap. So the question arises whether this material is really topological or it's conventional, and we can investigate that by moving the scanning tunneling microscope tip up to an edge and looking for that edge state. And when we do that, we find that there is an extra density of states which fills in the bulk gap. So the bulk gap here, this is on a logarithmic scale, has very low conductance, and then there's extra conductance at the edge. So that edge conductance persists over a range of energy, which is in the bulk gap, and it decays away from the edge into the bulk. And this lower panel shows the decay is exponential, and so that's the wave function of this edge state decaying into the insulating bulk. So we can verify that this is a topological insulator. This also agrees with DFT calculations for this material by two different groups, and so we think that that's correct. And we can apply an electric field with this STM tip. So we can bring the STM tip closer or farther from the surface and vary the electric field. When the tip is very far from the surface, we have a small electric field and we see a large band gap in this tunneling density of states. And then as we bring the tip closer, we increase the electric field, and that band gap actually, you can see, shrinks down to 0. So in the middle here, you get a nice V shape where the band gap has gone to 0. But then beyond that point, actually, it opens up again. So amazingly, with electric field, the band gap's non-monotonic, has a non-monotonic behavior, closes to 0 and then reopens. And that's actually exactly what's theoretically predicted. So we think that this electric field is untying these knots in the topological band structure. And we can plot a phase diagram of band gap. This is band gap in EV, not milli electron volts. Band gap in electron volts versus electric field, and in fact, it closes down and then reopens again. And when it reopens, it's a trivial insulator, and this would be the off state for a transistor. Whoops, I've done something funny. What happened? There we go. Okay, so lastly, I'll see if in just a few minutes, I'll tell you about probing the topological edge conduction. So I've shown you that we can make this nice material, sodium-3 bismuth, which is a large bandgap topological insulator, but we'd like to see what's going on the edge. So we can grow this material on an insulator. So the films looks something like this. So we can get nice films that have a collection of 1 and 2 layer regions. It's not quite as pretty as the films on silicon. And we're growing this actually through a mask. So we can make a little device that's connected to electrodes that's available to do transport experiments, all in vacuum. And so the kind of experiments we'll do, we want to see when the transport is along the edge. So we can do a regular resistance measurement where we run current through the middle of the device and measure voltage on the voltage probes. Or we can run current through one corner of the device and measure voltage at a distant point. If the material is a bulk conductor, we expect essentially no voltage here. But if the material conducts along the edge, then there will be current that will run all the way along the edge and create some voltage here, which will be comparable to the local voltage. And so what we're going to do, our material actually starts out a little bit n-doped, and we have to hole dope it with this molecule F4TC&Q to get the Fermi energy into this topological band gap. And then as we do that, we can measure this local resistance and non-local resistance. And particularly, we probe their ratio. And so if it's a bulk conductor, we expect that ratio to be 10 to the minus 3, and it is before we start doping it. And after we dope it a little bit, we find that that ratio goes to about 1, which shows us that the current is actually running only on the edge of the material. The resistance is not 0 in this state. It's still resistive, but it's not ballistic over the millimeter scale of our device. Maybe that's not surprising, but it is ballistic over 100 nanometer scales, which is really not bad. So in terms of device, ultimate device scales, it's already ballistic over 100 nanometers, which is plenty. The IV curves become very unusual in this regime. At low current, we see this non-local to local resistance ratio of 1. So we have edge state transport, and then we apply higher and higher current. Eventually, the bulk breaks down, and we get current shorting through the bulk, and so we lose our non-local voltage signal. So that's exactly what's expected for edge state transport. This gap is around 150 millivolts, and that's probably something around the the bulk gap of the topological insulator. So lastly, I said the edges are a little bit resistive. The idea that people have is that the edges are being scattered by some probably electrons and quantum dot puddles that are inside the material, and so those act as little magnetic scatterers. So an electron comes along and it scatters off this local moment, this local spin in the material, and then it can move backwards. So if that's the case, actually, we can suppress that kind of scattering with a magnetic field, and we've done that experiment. So when this material is a bulk conductor, it actually shows positive magnetoresistance due to weak anti-localization. And then the red curve is the experiment when the material is in the edge state conduction mode. You can see the resistance is rapidly dropping towards zero as you increase the magnetic field. This is actually 0.9 Tesla, it's a very small magnetic field. And then we've done the theory for this. And so if we can include only magnetic scattering and we include the fact that this is a chiral edge, so it's a topological edge, then we get the blue curve. You can see the resistance should drop to zero. And then if it's a sort of hypothetical metal that has only magnetic scattering, but it's not chiral, you'd get the green curve. And so this shows you that the material must be chiral, so it must be topological edge that's doing the conduction. And in fact, we'll be able to really kind of force that resistance to zero by suppressing spin flip scattering. And so there's only one fit parameter here, which is the G factor, which is huge for this material because it has very strong spin orbit coupling, but it's in very good agreement. All right, so let me conclude. We're interested in making this topological transistor to reduce the energy used by transistors, and I've shown you one. We're really starting out at the beginning with new materials, and I've shown you one material that could work, which is this sodium-3 bismuth, and it could work. It has a very large band gap and could work at elevated temperatures. Okay, and I'll put up some acknowledgements. There are some references here for people who are interested, and thanks.
Thank you, Michael, for the great talk. It's really interesting to see the steady progress on getting edge state transport. I think it'd be eye-opening for a lot of people to see the rate at which data centers are consuming electricity and how rapidly that consumption is growing. Well, in the interest of time, we have to move forward with the discussion session now, and I would encourage anyone who has any questions for any of the three speakers to please use the Q&A pop-up window to send it our way. And if the three speakers could or confirm that they're online, that would be great. So Paolo, are you still with us?
Yes, I was on mute. Yes, I'm online.
Excellent, excellent. All right, great. So I'll hand over to Francesca.
Great. Thanks, David, for introducing the panel discussion. And yeah, thanks to all the speakers and fantastic talks. And you really can see how the technology is improving, I mean, in all ways, in terms of novel architectures, now quantum, in terms of we're going from 3D materials to 2D materials to edge materials to one atom material. So it's really getting it to the edge of what we can do. That is fantastic, but I'm sure there will be so many further developments. So to start off our discussion, and please from the audience, do send more questions. We have a few already that we were going to discuss, and continue sending questions, and we'll take it into our queue. So I wanted to start with this question because I think this is something that sums together all of the talks today, and also it puts it into the context of semiconductor industry, which is the industry of electronics has been so far. So I'm very familiar with that because I've been working in academia and also in industry in the semiconductor R&D. And of course, I'm very well familiar with the fact that the R&D in semiconductor industry needs very long lead times, 10 to even 20 years in order for a new technology to make it through into application. And I say 20 years is not unusual, especially when we get into quantum, where not only the materials, the devices, the packaging, everything has to be reinvented, but even the software. And Michelle is very aware of that. So it's a huge value chain that has to be prepared. At the same time, so in order for that to happen, the semiconductor industry needs also early visibility into all new potential solutions, so very long before they can be implemented, because of all these lengthy iterations that are required to assess the suitability, reliability, scalability. So all of that needs very close and early collaborations between the academic side and industry. So what I'm getting at is that usually, naturally, the research community and the industry community tend to be relatively separate, attend different conferences, operate into different circles, and the communication between each other, especially at the early stages of technology, is not that easy. So I was going to ask to all of you, starting with Paolo, then moving through Michelle and Michael, how do you think that this cross-pollination between the two groups, two communities, can be improved? And where are the major bottlenecks for this to happen? So Paolo, maybe you can start and give your perspective from industrial side, R&D, and also linking it to the RRDS.
Yeah, thank you, Francesca. In my past experience, it's very important to place people from the industry into the research environment for extended periods of time. In that case, they can evaluate directly, hands-on, the status of a given technology and assess the probabilities that this technology can be actually feasible in a reasonable amount of time. For instance, even though it's a much less complex problem, but when we were to engineer the FinFET and all these elements, the key element I did was to send researchers in different parts of the world where this research was in progress. So, for instance, EMEC in Belgium was doing something, Berkeley was doing something, Stanford. It was convenient given my location, but nevertheless, we put many researchers so that people could speak the same language. Sometimes we just read papers that we publish, but they're very cold. It's difficult to see what's behind it. And so programs that encourage extended periods work in either way. I had researchers also from research organization in Intel for 2 or 3 years, to work on some project. People are really the key to really foster this exchange of information, and especially, technologies that are beginning to look very interesting, like what Michelle has been doing with silicon. It feels so close to me, that the things that she's doing, that it seems, I can stretch my hand and grab it almost. Okay, I know there is a
come over here, Paolo. Come and stay with us.
Okay, but that's a sense, I saw your videos on YouTube and so forth. This looks so familiar, right?
Yeah.
And on the other hand, besides, I only mentioned the tunnel transistor, but we initiated also activity in topological insulator and another activity. In fact, for the last 10 years, I was the chairman of the advisory committee from Berkeley, since they had several of this program on magnetics, and they realized very fast switch times. I feel that we are in a period that is very prolific, but since many of the big companies like Samsung, TSMC, and Intel are so busy pushing the existing technology, they have lost a lot of this connection. That when I was there, 15 years ago, I had a group that was specifically dedicated to this. But most of these people now work in development. Only a few go to SRC to listen to the report, and so we lost this bridge. And I feel that's missing in this moment. So, I've been trying to get IEEE at least to organize some forums, similar to what you're doing, Francesca, but more extended. So, for instance, we're going to have one on networks, that is not just 5G, but in August, where we invite people from the industry and people that are doing research in communication, because there is so much hype, and I don't think there is enough substance. And, I would like to do the same with this kind of activities, like extend what we've done today, but maybe with the 30 people that can spend 2 days discussing this element and outline next steps. So IEEE is a little conservative. They want to do publication and conferences, but then they are very afraid to organize a forum. So I've been doing them quietly to see if they get used to the concept. So I hope in the next couple of years we can have an extended forum where we can compare notes, because many of the researchers that both you, Michelle, and Michael are doing, I think we could contribute, doing experiments in a much shorter time that you can, maybe not as sophisticated, but at least we can find out what wiggles, and if something wiggles, then all of a sudden the situation changes completely. So that's would be my wish, okay?
And thanks, Paolo, for that. I think I can relate totally to what you say. We've been pushing certainly from the EDS side, and I think we got some good signals that they're starting to appreciate more and more this type of interactions, and this fits in within the IEEE mission. So I'm sure that will happen more and more. But as you said, it also depends on individuals, and the change, I've seen it through my experience at IMEC. It's changing even IMEC since 20 years ago. It's changed so much. The whole landscape has changed. And I also wanted to pass this question on to Michelle and see her point of view, also because she's also involved in the Australian quantum roadmap. And so ask same question to Michelle. Michelle, how do you see this interaction between industry and academia? What are the plus points and the bottlenecks that you have been experiencing?
Sure. Look, I think so. Look, I really have been in the field for a long time. But back in the 2000s, when I first started in the quantum computing field, I actually reached out a lot to SRC, Semiconductor Research Corporation. I was involved in a lot of their ITRS roadmaps for a guy called Dan Herr. And so I did get a chance to go to the US. We got funding from the SRC to deal with some certain issues that I've already published. So the making very narrow wires that are highly conductive. I got, as a consequence of being part of that roadmap, so I really, part of that group of people I found it fantastic. They actually got us together with IBM, and we had a series of tutorials to our group from IBM, from a guy called Wilfred Hench. And so he literally went through how is a silicon transistor made from start to finish. And so a bunch of tutorials to my group in Sydney from him, which was fantastic. I think even IEDM, so I've given talks at IEDM and I've given tutorials on quantum computing at IEEE in the US. So there has been that link, which I've thoroughly benefited from. But Paolo's right, it has kind of, for me, it feels like it's dropped off more recently. I don't know why that is. So we could reignite that and certainly I think quantum computing, we actually got it listed on the roadmap as one of the technologies to discuss more and grow. So that's something I'm definitely keen on. But I think, yeah, ultimately having industry people working closely with us is quite valuable. So if there is a program in the US like that where they can still continue that, I don't know if it still is continuing, but that would be fantastic. And we'd certainly engage very heavily with that.
Great, thanks, Michelle. And as I said, yeah, IEEE for sure will have more and more activities in this field. I think is behind our ideas, but I think that there's much more that we can certainly do. So hopefully also locally here, we will do what we can.
Yeah, sounds great.
Michael, so same question to you from your perspective.
I'll be brief. I'll put in a plug for multidisciplinary research centers. I think of course it's very important to put researchers from different fields together and to have collaborations with industry. And of course those have to also evolve, right? That you have to, it's going to be different groups to solve different parts of the problem as the problem evolves along. Yeah, I mean, I also think I feel that there has been some shift in the semiconductor industry, almost a giving up on device level advances, which I think Michelle's working on and I'm working on. Essentially, what is the new physics down at the device level, and more, as Paolo has said, the advances over the next, in this period and the next 20 years in silicon CMOS are going to be more focused on architecture and going to 3 dimensions and integrating and multiple cores and all these things, right? So, and so that's pulling people apart. And I think we need to kind of try to put people back together again. So anyway, I certainly recognize the need, and hopefully we can do that.
It is a very good point indeed, and maybe I can tease a little bit Paolo because so I've been kind of part of the ITRS and now also IRDS. So IRDS is now International Roadmap of Devices and Systems. So the systems is something new that didn't used to be in the previous roadmap. So maybe Paolo, you can comment a little bit more about that.
Yeah, I'm actually, I believe I wrote something for the EDS, for the IEEE letters, and we're gonna have a set of articles, so the different chapters of the IRDS, trying to rebuild, the community in some way. And, the foils that I showed today, about the connection with the quantum and the connection with the advanced transistor for the last 2 or 3 years, I've been including them in all my presentations. It's not something that I did just because of this meeting. This was very opportunistic, but it's something that I believe it's in the range that is, I don't say mature, but it's close enough, there are enough results that if the structure was the way it used to be around 2005 and so forth, it would be, I would have a couple of assignees on location working on this, okay, that I cannot do nowadays. So many of the companies where initially, my office was 2 offices from Gordon Moore. So I had the opportunity of talking to these people that were really the initiator. And Gordon was a techie, whenever there was something technical, he was really interested. And then progressively around 2005, 2006, with all due respect, the MBAs began running companies. And their attitude is, how do I make more money? Can I cut R&D and put more money in products? I don't mean to be disrespectful, but that's their attitude. So in 2006, we began seeing a scale back. In 2009, Craig Barrett, who was professor of material science at Stanford and chairman of the board, retired. And by 2012, I had to argue for any money or research and so forth. So I said, okay, maybe I can do better something outside than inside. So unfortunately, this is highly predicted. Each company starts with the founders, the techies, and then the MBAs take over. And their mentality is not, forgive me, very scientific, okay? It's just how much money do I make in the next quarter? But fortunately, if we keep repeating this alarm that the world is coming to an end in 2030 and we can do something about it, at least the US government has reacted positively on this. I've been doing this mysterious presentation. They say, can you make a presentation? Somebody in the government wants to hear it. I don't know who they are. I just make a blind presentation. And I say, we could do something in quantum computing more like 2 years ago, then, I'm not saying they are the only one, but then this QEDC initiative comes all of a sudden. So it's a slow process, but at least if you keep advertising and repeating the message, eventually something happens. And I hope in the next 2 or 3 years, we can actually do something with the money, because the risk is there's so much hype and people are going to be disappointed in the next 2 years. And so we need to do a soft landing. If we do a soft landing, we present few concrete results and few association. Right now, people expect, incredible things. If you remember the beginning of the NNI, the IC is going to build a bottom up by itself. That was lunacy, okay? But everybody that would say that would get money. And so until 2006, 2007, everybody got funded with this. And then progressively we began showing that FinFETs were workable. So people lost some enthusiasm from this bottom up, even though we stole a lot from atomic layer deposition. We stole a lot of the techniques. It just we didn't apply precisely the way they expected, okay? And so, Michelle, if I see your position, so forth, I think we can almost, build some custom devices for you, and then you make some sense out of it, okay? Just we wouldn't know what to make of it. But the technology are beginning to merge. I know that I saw your video is very difficult to place the atoms, But we have way of opening holes that are like 1 nanometer, then you can shower them in some way. So I think this bridge is missing for the time being. The best we can do is to advertise it, and eventually something moves completely outside our control. But I have the feeling that something needs to happen, and it needs to be less hype and more realistic in order to have a continuous process going forward. Okay.
Thanks,
So-
Paulo.
So
So
can
go ahead.
yeah, just I think, look, I think it's true. I mean, the whole comment about the MBAs taking over, it's terrifying, to be honest. And it certainly seems to be happening a lot in the US, and we have fewer companies over here. So we're kind of watching how it works over there, and it's quite interesting. But I think, so just going back to your comment about the placing, I mean, very keen to interact, Paolo, honestly, because I know some of the stuff we've done on atomic layer deposition is being picked up in different ways. But the concept, I think, of scanning probe as being a difficult thing, it isn't actually very difficult. So our yield of devices is incredibly high, and the speed at which we can make them, obviously we don't make millions at a time in terms of mass production, but the good thing about it is it's reproducible. So one of the things about the quantum field is if you want to make anything, it's got to be reproducible. You've got to be able to make the same thing twice with a high certainty you're going to get it. And I think that's the challenge in quantum, is that there's very few techniques that have the precision to make it reproducible. Anyway, so I'm very keen on talking to people with industrial backgrounds about scaling up that reproducibility, because I think that's going to be key.
And let me
So
add something else for a moment, quickly. I've also, since 2017, I began working with the roadmap that used to be 5G, but then we changed the name to INGR, International Network Generation Roadmap, because if I look ahead, okay, you cannot have a quantum device in your pocket like you have your cell phone. There will be placed in similar location like data center.
Yeah,
And
absolutely.
so if you don't have a network that is extremely efficient, and it's not the network for the cell phone, you're not going to do quantum calculation on your cell phone. It has to come to the home or to a different place.
Yeah.
And so all the approach that I'm supporting there is fiber optics everywhere, so you can have it directly, this communication to what are the data center that become quantum computing center.
Yeah.
And so in this way, the technology can be used, because I think people will be disappointed. There will be few, quantum computer that, the big companies own, but the normal people, the consumers say, what does it do to me, right?
Yeah.
And so if we don't reach the consumers in some way, then we're not going to have the support that we would like to have. And that's why this work on the communication beyond the 5G phone, that I think is going to be a flop, because how much can you do with the phone? You're not going to watch, a high definition movie while you're driving in the car, right? That's the last thing you want to do. But when you are at home and you have your 80-inch TV and you want to, really analyze something or so forth, then, the information doesn't need to be in your basement, can be miles away, as long as you can quickly connect it, okay? So there are many bits and pieces of this puzzle.
Yeah.
They seem not connected, and the best we can do, is connecting the pieces. And then somebody say, oh, of course, that's the way it was, right? The usual journalist and publish something, overnight success. And we work on it for 20 years, right?
Paolo, this is actually a wonderful segue to the next question, which comes from the audience, which David is going to.
Yeah, so Paulo, you made several interesting points. Of course, quantum technology, Samsung has just released the first phone with the quantum random number generator in. So in some ways, it's entering into the corporate or the commercial world now, maybe not quantum computation, but quantum technology more generally. And this leads on to a question from Jennifer Wong Leung at ANU. She says, firstly, thank you for the wonderful webinar. And, the first quantum computing devices have been shown to work at about 0.5 Kelvin. But her question is, of all the various different technologies out there, which are the most promising to operate at room temperature? And would any become a replacement for devices that we currently have, like laptops, iPads, etc.?
So I'm happy to take that on. I mean, to be honest, I put up the 7 different platforms, material platforms. There's probably many more than that, but I guess it all comes down to the materials technology. So there are some materials such as diamond, which works at room temperature and arguably is optically addressable. So it sounds fabulous, yeah? And everyone would think, why don't we just do diamond and forget everything else? But diamond is very hard to manufacture. So pretty much every material has a bunch of strengths and a bunch of weaknesses. I think even the semiconductor devices that have been shown to operate at higher temperatures, certain aspects work at high temperatures, but not everything. And so it's critical in the quantum computing field that you are able to input information, read information, get coherent single and 2 qubit gate operations. And all of those, every aspect of that has to be above what we call the fault tolerant limit. So there's a 99.9% fidelity that you've got to get above for that to work as a computer. And the issue is that you can hit one of those or two of those, but you've got to hit all of them in one device. And so that's the challenge. And at the moment, it's the Paolo's talking about it, but the kind of hype in the field is like every little result comes out like it's a big thing, but actually it's all got to work on one platform. And at the moment, there is no obvious, hand on heart platform. For me, I only have one life, so I've dedicated it to the one that I think is going to hit every one of those, which is the atoms. And the atoms are kind of like the ion trap equivalent, but in a semiconductor material. But if you had any other platform person here, they would tell you that theirs is the best, yeah. So that's life, and honestly, none of us know until we've done it. So we're all going to keep pushing on those technologies. But I guess the caution is that ultimately every aspect's got to be fault tolerant. The input, the output, the coherence time, the single, the 2 qubit gates, and then when you scale to 100, is 100 going to behave the same way that 10 does? Until you've done it, you can't say. So it's and so back to the final. I'm a long answer. Sorry about this, but the final bit about. Are you going to have it on your iPads and phones and everything? At the moment, Paolo's right. It's going to be a quantum computer server center that you access, kind of like the original data centers. And so that communication to that and the ability to have a controlled environment. At the moment, we believe it's going to have to be millikelvin. It's going to be very hard in a semiconductor to scale without millikelvin. So you are going to have some well-controlled environment, some kind of server farm, which is what we're trying to create here, where people can then access remotely.
So Michael, leading on from that, I mean, it seems in some contexts, classical computers are here to stay. For the foreseeable future, we'll be using laptops and iPads for our personal kind of stuff. But what do you think we'll see in the next decade in terms of reducing the energy consumption of these type of devices? Do you think there's scope to see a decrease in the greenhouse emissions associated with these things, or is that unrealistic unless the industry has big changes?
Yeah, I mean, to answer the first part of Jennifer's question, we've decided to focus on devices that have the prospect of working at room temperature, and because we're focused on classical computing, which we think has to persist, there will always be classical computers. So quantum computers are always going to be serviced by some classical computer that feeds information in and out, and so we do need classical computation. A lot of it's going to have to take place at room temperature on your laptop or in your phone. And so we've focused on that. I think, in terms of what I laid out in terms of energy consumption and computation, we do believe that there's going to be a period of crisis and fairly rapidly increasing energy that's used in computation. I mean, that it's already something that's noticeable. I mean, computation, ICT uses about 8% or 10% of the electricity in the world right now, and that is growing faster than any sector. And so, and we think that will become more pronounced as it becomes more difficult to make energy efficient chips. And so there's going to be a bit of a gap. Our technologies are not going to be ready, for a decade or perhaps more. And so I think at that device level, reducing the energy that's used in every individual computation it's a difficult problem, and it's going to take some time. But ultimately, if we want to continue to be able to use more and more computing, we need to do it. And so that's why we're trying to do it now.
All right. Well, I should thank everyone who was able to come and take the time to be with us today. Michelle's got a very busy schedule, so she needs to leave at this point. I think we should thank all the speakers again for a fantastic session, and hopefully we can do something like this again, to think about forming those bridges between academia and industry and thinking about translating things more quickly.
I think this will require lots of iterations, and we will be happy to help there. So Michelle, thanks so much.
Thank you, everyone. It's been fascinating.
Thanks a lot. And Paolo, thanks so much also for joining us from California.
Yes.
Hope it's not too late there. And
Thank you.
thanks to the audience. And we're looking forward to have another session like this to discuss this further. There's so much discussion to be had still. So thank you. Thanks a lot. Thanks, everyone.
Thank you.
Thanks for having me.
Bye-bye.
Thanks.
Bye. Bye.